August 12, 2000. The Barents Sea. A shockwave equivalent to 1.5 tons of TNT rips through the freezing Arctic waters. On the surface, the massive cruisers of the Russian Northern Fleet shudder as a dull thud echoes through their hulls. On the seabed, 108 meters down, the pride of the Russian Navy, the K-141 Kursk, is dead. But for the world, the nightmare was just beginning. The Kursk wasn't just any submarine. It was a 154-meter-long Oscar II-class Titan, twice the length of a Boeing 747 and weighing nearly 18,000 tons. It was a city under the sea, designed to be the ultimate carrier killer. Now, it was resting on the bottom of the ocean with 2 nuclear reactors, a hold full of cruise missiles, and a ticking clock of international scrutiny. Most salvage operations are about recovery, but this was about surgery. To bring the Kursk home, engineers had to do the unthinkable. They had to build a giant 26-armed hydraulic claw, saw the bow off a nuclear vessel while it sat on the seafloor, and lift it using a custom-built barge that cost $65 million just to mobilize. This is the story of the most complex, high-stakes salvage operation in human history. To understand why the salvage was so expensive and technically daunting, you have to understand the sheer scale of the ship and the violence of its end. The Kursk was marketed as unsinkable. Its double-hull design meant it featured an outer hydrodynamic shell and an inner pressure hull made of high-nickel, high-chrome steel. This 2-inch thick inner hull was designed to survive a direct hit from a torpedo. But on that August morning, the Kursk didn't face an external enemy. It faced a chemical catastrophe from within. During this summer 2000 naval exercise, the crew prepared to fire a practice-type 65 Fat torpedo. These weapons ran on high-test peroxide, or HTP. While highly efficient, HTP is terrifyingly volatile. A faulty weld in the torpedo casing allowed the HTP to leak, reacting with the copper and brass in the torpedo tube. The resulting chemical explosion didn't sink the ship instantly, but it gutted the forward torpedo room and killed the crew in the first compartment. 2 minutes and 15 seconds later, the heat from the initial fire reached the remaining live warheads. The second explosion was so massive it registered on seismographs as far away as Alaska. It ripped a jagged, gaping hole in the bow, instantly flooding the first 5 compartments and sending the Titan to the mud. The political stakes were just as heavy as the physical wreck. Vladimir Putin, then a new and relatively untested president, faced a grieving nation and a furious international community. While 118 men were on board, 23 had survived the initial blasts and retreated to the sternmost compartment 9. They waited for a rescue that never came, trapped in the dark as oxygen ran out. Once the site was confirmed as a graveyard, the Russian government faced a dilemma. Why not just leave it there? The U.S. Navy often leaves its lost subs as war graves, but the Kursk was a different beast. 2 650B pressurized water reactors were sitting in a crushed hull. If the structural integrity failed, the Barents Sea fishing grounds, vital to the Russian economy, could be contaminated for decades. Furthermore, the Kursk was armed with 24 P-700 Granite cruise missiles. The Kremlin could not risk Western intelligence vessels accidentally stumbling upon their most advanced missile technology. A promise was made to the families. The sons of Russia would be brought home, and the sea would be made safe. In late 2000, the Russian government invited the world's best salvage companies to bid on a project many experts deemed impossible. The wreck was too heavy for any existing crane. The weather in the Barents Sea was notoriously violent, and the bow was a mangled mess of unexploded torpedoes and jagged steel. Any attempt to lift the ship as one piece ran the risk of the bow snapping off, which would cause a catastrophic shift in weight, potentially flipping the salvage barge or rupturing the reactor compartment. This is where the Dutch consortium of Mammoet and Smit International entered the picture with a plan that sounded like science fiction. They proposed a clean lift strategy. They would amputate the damaged bow and leave it on the seafloor, then lift the remaining 90% of the ship vertically using a massive hydraulic system. The primary engineering nightmare was the saw. Before the lift could happen, the bow had to be removed with surgical precision. But how do you cut through high-tensile Russian steel in a double-hull structure under 100 meters of water? The Dutch designed a massive, custom-built diamond wire saw. It functioned like a giant cheese cutter, utilizing a cable studded with vacuum-brazed diamond beads. This cable would be pulled back and forth by large hydraulic cylinders positioned on either side of the hull. However, the operation was a gamble of the highest order. The bow was still filled with those unexploded HTP torpedoes. If the saw generated too much heat or struck a sensitive warhead, the salvage crew wouldn't just be out of job, they'd be vaporized. This was the environment into which the divers and engineers descended, a place where 1 centimeter of error meant a nuclear-scale disaster. To prepare for the actual lift, the Dutch engineers had to transform a massive flat-top barge, the Giant 4, into a specialized salvage platform unlike anything the maritime world had ever seen. The sheer physics of the operation were daunting. They weren't just lifting a dead weight. They were lifting a 9,000-ton section of a nuclear submarine through a column of water that would create immense drag and suction. To handle this, the Giant 4 was outfitted with 26 massive hydraulic jacks, each capable of pulling 900 tons. These weren't standard cranes. They were strand jacks that utilized bundles of steel cables or strands, which would be pulled up in synchronized increments. This created the giant claw effect. The jacks were connected to a sophisticated computer system that monitored the tension in every single cable. If the wreck began to tilt, or if a sudden undersea current increased the load on one side, the computer would compensate in milliseconds to prevent the cables from snapping like guitar strings. Before the claw could be attached, the most dangerous part of the job fell to the saturation divers. These men lived for weeks in pressurized chambers, breathing a helium-oxygen mix that made their voices squeaky but allowed them to work at depths that would crush a normal human. Their mission was to cut 26 precise holes into the Kursk's double hull, 13 on each side. These holes had to be perfectly aligned with the submarine's internal frames to ensure that when the lift began, the hooks wouldn't just tear through the outer casing like paper. Working in near-total darkness, with visibility often limited to a few inches due to silt, the divers used high-pressure water jets and thermal lances to pierce the high-tensile steel. Every move was shadowed by the knowledge that they were working inches away from the shattered remains of the torpedo room and the delicate, lead-shielded walls of the nuclear reactor compartment. The amputation of the bow was the next critical hurdle. The custom-built diamond wire saw was lowered to the seabed, anchored by 2 massive suction piles, huge steel cylinders that sucked themselves into the mud to provide a stable platform for the sawing machinery. The diamond-beaded cable was threaded under the Kursk's hull, between the first and second compartments. For days, the hydraulic cylinders pulsed, dragging the cable back and forth. The friction was immense, and the risk of the wire snapping was constant. More terrifying was the threat of sympathetic detonation. If the saw hit a piece of jagged debris that sparked near a leaked torpedo warhead, the entire site could explode. Engineers monitored the vibration and heat of the cut with the intensity of surgeons. Finally, after days of grueling, slow-motion labor, the cable broke through the top of the hull. The mangled bow was officially severed, left to rest in the silt as a radioactive crime scene, while the rest of the ship was now free to be raised. With the bow removed, the Giant 4 moved into position directly above the wreck. This was the moment of truth for the $65 million investment. The 26 claws, massive custom-forged steel hooks, were lowered on their strand cables and guided into the 26 holes the divers had cut. Each hook had to be locked into place by the divers, ensuring they were gripping the primary structural ribs of the submarine. This was high-stakes salvage in its purest form. If even one hook failed during the initial breakout from the mud, the resulting zipper effect could cause the others to fail in rapid succession, dropping the Kursk back to the seabed and potentially cracking the reactor vessel wide open. The world's media watched from a distance as the order was given to take the strain. The breakout from a seabed is the most precarious part of any salvage. The suction of the mud can effectively double the weight of the object being lifted. On the Giant 4, the hydraulic jacks began to moan under the pressure. The tension readings on the computer screens climbed into the thousands of tons. For hours, nothing seemed to move. Then, slowly, the sensors detected a change in pressure. The Kursk was moving. It wasn't a sudden pop. It was a microscopic shift, a few millimeters at a time. As the 9,000-ton hull finally broke free of the Barents Sea mud, the barge groaned as it took the full weight. The giant claw had done its job, but the operation wasn't over. Now, they had to transport a 500-foot nuclear submarine, suspended precariously beneath a barge, through 100 miles of open, unpredictable Arctic Sea to the dry dock at Roslyakovo. The transit from the wreck site to the Kola Peninsula was a feat of nerve-shredding navigation. The Kursk was not sitting on top of the Giant 4. It was tucked into a specially carved saddle on the underside of the barge's hull. This configuration was necessary because the submarine was far too heavy to be placed on deck, and towing it through the water column would have created enough drag to snap the lift lines. For 15 hours, the flotilla moved at a snail's pace of just 3 knots. If the weather turned, a common occurrence in the Barents Sea, the heavy swells would have caused the barge and the suspended submarine to move out of sync. The resulting pounding effect could have hammered the Kursk against the bottom of the barge, potentially breaching the nuclear containment. Every radar sweep and weather satellite was monitored with obsessive focus, as the $65 million operation literally hung by a thread of steel strands. As the barge approached the Roslyakovo shipyard near Murmansk, the engineering team faced their final hurdle, the docking. This wasn't a standard procedure. They had to float the Giant 4, with the Kursk still hanging underneath it, into a massive floating dry dock called the PD-50. Once inside, the dry dock would be raised, lifting both the barge and the submarine out of the water simultaneously. It was a Russian nesting doll of maritime engineering. There was less than a meter of clearance on either side of the sub as it entered the dock. The tension in the air was thick. After months of planning and weeks of sea work, a single gust of wind or a miscalculation in ballast could lead to a collision that would ruin the entire recovery. When the pumps finally cleared the water and the black, scarred hull of the Kursk settled onto the support blocks, a silence fell over the yard. For the first time in over a year, the Titan was out of the water. The sight of the Kursk in dry dock was haunting. The front of the ship was gone, ending in a jagged wall of twisted metal and severed pipes where the diamond saw had done its work. The investigators and recovery teams who entered the hull were met with a scene of absolute devastation. The force of the second explosion had been so immense that it had bent the massive internal bulkheads like cardboard. As they moved toward the rear of the ship, into Compartment 9, the atmosphere changed from one of technical curiosity to somber reverence. This was where the 23 survivors had gathered, hoping for a rescue that the world was too slow to provide. In the pockets of the officers, they found the final notes, scrawled in the dark, that provided the definitive, heartbreaking timeline of the crew's final hours. These documents confirmed that while the Salvage was an engineering triumph, the human story was one of tragic delay. The forensic analysis of the wreck provided the data the international community had been desperate for. The 2 nuclear reactors were found to be remarkably intact. Despite the violence of the explosions and the impact with the seabed, the automated shutdown systems had functioned perfectly, and the lead shielding had held. This was a massive relief for the Nordic countries, proving that the $65 million spent on the Salvage had likely prevented a long-term ecological disaster. However, the internal damage confirmed that the Type 65 torpedo was a widowmaker. The Russian Navy subsequently retired the HTP-powered torpedoes from service, acknowledging that the volatile fuel was too great a risk for even the most advanced vessels. The Giant Claw had not just recovered a ship, it had recovered the evidence of a systemic failure. Ultimately, the Salvage of the Kursk remains the benchmark for heavy-lift maritime operations. It proved that with enough capital, in this case, roughly $65 to $70 million in total, and a combination of Dutch engineering and Russian grit, almost anything can be recovered from the deep. The salvage sections of the Kursk were eventually broken down for scrap, with the exception of the sail, which was preserved as a memorial in Murmansk. The operation stands as a testament to a time when international cooperation overrode Cold War-era secrecy to solve a global nuclear threat. For the engineers at Mammoet and Smit, it was the job of a lifetime. For the families of the 118 sailors, it was the bittersweet closing of a chapter that had gripped the world's attention and redefined the limits of what is possible at the bottom of the sea. The engineering philosophy behind the giant claw was born out of a necessity to overcome suction tonnage. When a vessel as massive as an Oscar II-class submarine settles into the soft clay and silt of the Barents Sea, it doesn't just sit on top of the mud. It becomes part of it. The seabed creates a vacuum seal around the hull that can add thousands of tons of virtual weight to the lift. To break this seal, the Mammoet Smit team couldn't simply pull upward with raw force. They had to vibrate and wiggle the hull using the 26 strand jacks in a pre-programmed sequence. Each jack was a marvel of hydraulic precision, utilizing bundles of 15mm steel strands that were gripped by upper and lower anchor blocks. As the cylinders extended, the upper blocks would grip the cables and pull them up. As they retracted, the lower blocks would hold the load. This rhythmic, inch-by-inch ascent was controlled by a central computer nicknamed the Brain, which ensured that the giant barge remained perfectly level despite the shifting center of gravity below. While the world focused on the hydraulics, the survival of the divers remained the most harrowing human element of the $65 million price tag. These divers weren't just technicians. They were underwater construction workers operating in a graveyard. To cut the 26 holes for the lifting hooks, they used a specialized grit-water jet cutter that could slice through the inner pressure hull. However, the Kursk was covered in a thick layer of rubber anti-anechoic tiling, designed to make the sub invisible to sonar, which would melt and clog the cutting tools. The divers had to peel back these heavy rubber sheets by hand, often while battling surge currents that threatened to slam them against the jagged steel of the wreck. Every hour spent at 100 meters required days of decompression in the hyperbaric chambers aboard the support ship Mayo. The psychological toll was immense. They were frequently working in the very compartments where the 118 sailors had perished, moving through debris that included personal effects, clothing, and the haunting remnants of a crew that never had a chance. The diamond wire saw operation itself was a masterclass in patience. The wire was actually a high-strength steel cable fitted with thousands of industrial diamond rings, separated by springs to allow for flexibility. Because the Kursk was a double-hulled vessel, the saw had to cut through the light outer hull, the heavy internal frames, and then the high-tensile inner pressure hull, all while maintaining a perfectly straight line. If the wire jammed, the entire operation could have been mothballed. To prevent this, the engineers used two suicide suction piles, massive 12-meter steel tubes, to anchor the guide pulleys for the saw. These piles were sunk into the seabed on either side of the bow, providing the leverage needed to floss the diamond wire through the ship. The noise of the sawing was described by sonar operators as a constant, low-frequency scream that echoed through the Barents Sea for days, a mechanical dirge for the fallen vessel. Once the bow was severed and the lift began, the weight on hook data became the most scrutinized numbers in the maritime world. As the Kursk was pulled toward the surface, the buoyancy of the ship changed. Because the submarine was still partially filled with air pockets and various densities of fuel and water, its weight was not static. The computer system had to constantly recalculate the tension on each of the 26 jacks to prevent the hull from twisting. If the hull twisted by even a few degrees, it could have sheared the lifting hooks or worse, cracked the reactor shielding. To mitigate this, the Dutch team used a heave compensation system. This acted like the suspension on a car, allowing the cables to extend and retract slightly in response to the swell of the waves on the surface. Without this, the vertical motion of the giant four on the waves would have acted like a giant hammer, jerking the 9,000-ton submarine up and down until the cable snapped. The logistical scale of the $65 million mobilization is often overlooked. To support the giant four, a fleet of tugs, survey vessels, and nuclear monitoring ships formed a steel ring around the site. The Russian Navy provided a massive security perimeter to keep away curious NATO vessels and environmental activists. Inside this perimeter, the operation was a 24-hour-a-day race against the weather. The weather window in the Barents Sea is notoriously short, usually closing by late September when the autumn gales turn the Arctic into a washing machine of 30-foot waves. If the Kursk wasn't secured in the saddle of the barge by the time the first major storm hit, the entire project would have been a total loss. This pressure led to a grueling pace, with engineers and divers working in shifts that pushed the limits of human endurance, all while knowing that a single spark near the severed bow could trigger a detonation of the remaining torpedoes. The final triumph of the operation, the entry into the Roslyakovo dry dock, was a moment of profound technical relief and political theater. As the PD-50 floating dock began to rise, the water drained away to reveal the true extent of the damage. The Kursk was covered in orange-brown silt and marine snow, but the sheer scale of the ship still commanded respect. Investigators wearing hazmat suits were the first to enter, carrying Geiger counters to ensure the reactors hadn't leaked during the transit. They found that the reactor scram emergency shutdown had been successful. The control rods had dropped into place the moment the first explosion rocked the ship, a final act of duty by the engineering officers on board. This discovery saved the Russian government billions in potential environmental cleanup costs and validated the decision to spend $65 million on the recovery. The legacy of the Kursk salvage is found in the DNA of every major deep-sea recovery operation conducted since 2001. It proved that the strandjack method was superior to traditional crane barges for ultra-heavy lifts. It also served as a sobering reminder of the dangers of HTP torpedoes, leading to their global decline in favor of safer electric or thermal propulsion systems. But beyond the data and the steel, the operation was about the 118 families. By bringing the ship back, the Giant Claw allowed for the recovery and identification of nearly all the crew members, giving them a burial in Russian soil rather than an anonymous grave in the Arctic mud. The $65 million was, in the end, the price of closure, a staggering sum spent to reclaim a piece of national pride and to answer the questions that had been buried 100 meters deep. The Kursk was gone, but the Giant Claw ensured its story would be told with the accuracy and respect that only the truth and 18,000 tons of salvaged steel can provide.